Hello, everyone. Thank you for joining us in today's webinar. Our topic today will cover 5 common issues that impact the success of training computer vision algorithms to achieve a performance state, least success, and provide value to your customers. We will provide a brief overview of each one, discuss a few considerations to prevent and overcome some of these issues, as well as provide you with a solution to consider in tackling these 5 common issues. After that, we will have an open Q&A session for everyone to ask any questions or any comments regarding the content as well as the demonstration that we will provide. My name is Ario Sanchez. I'll be the moderator for today's webinar. I am the Director of Business Development for Rendered.ai. My experience goes a little bit over 2 decades providing products and solutions to customers for geospatial data processing, as well as capabilities to automate the extraction and sense making and workflows for the users. Joining me today is our lead solution architect, Dan Hedges. His experience goes beyond a decade helping customers in many industries to extract knowledge and value from remote sensing data. Now, you probably have seen many of these articles or have read them, and you might have heard a lot of studies that have been conducted regarding AI. And they all highlight the dependency on the data, cost, time, as well as the skilled personnel required as you apply new technologies to any algorithm or any model you're attempting to train. Each model has its uniqueness, each data type as well. And this is something that requires the proper analysis of the results, as well as tests to be properly conducted to ensure that the results that you're getting are the correct ones. And all these forces together, they push and pull and impact significantly the success of your training. But ultimately, if any of them fails, or you have a significant deficiency on one, or one overpowers the other, success may not be achieved in the training of your model. So let's go into some of the challenges that we commonly see, or at least that when you look at all these studies and experiences that we might have all had are most common. So we'll start with the first one, data acquisition. And this one, it can be very challenging because even when the data is readily available, it may lack the diversity as well as the complexity to ensure that the robustness that you're seeking within your model can be achieved. Also, when it comes to attempting to do classifications as well as any kind of tests, you may not have sufficient data to get you the results that you're looking for, as well as achieve the necessary parameters that you're trying to look for. And when it comes to off the shelf, a lot of the pre-existing data may not be accurate. Also, it may lack the specific use cases in which you're trying to train your model. But to get real data is a very costly endeavor and can also take time. And when it comes to the real data, not only is collection or acquisition of the data important, but also ensuring that you have the right labeling and it's 100% accurate to ensure that the model's being trained on the correct things. Also, you may lack diversity. That could be very difficult to train the model. You need to have a wide range of variety in the data to make sure that it can encompass all the necessary scenarios that you're trying to train your algorithm against, and also any potential variations for the objects in which you're attempting to train the model on. With that then comes time requirements. A substantial time of training is needed to get the cross-validation necessary to evaluate your machine learning model and make sure that any technique that you apply as it goes through the training and all the subsets of data, as well as anything that you need to ensure that you get the variability necessary, that process could be lengthy. especially when your model is very complex and you have a lot of data towards training that particular model. You're going to require multiple training cycles. And this one, each one of those cycles is going to require validation of the data. It's going to require for you to train. It's going to require for you to do it over and over and over again to make sure that you achieve the level of or the success or parameters that you're attempting to achieve every time you train the algorithm. And most importantly, what adds time is the complexity of the model. The higher the number of parameters that the model may have, the longer it's going to take for you to train. Additionally, some architectures require more time to train. That is a de facto issue of these models. And not to forget, you also have to apply the computing resources, which may also increase your time. Data annotation is critical. It's essentially the backbone of everything that we do today when it comes to a lot of the AI applications that are available. And without it, the systems cannot process effectively. And if they do so, it can potentially cause problems because you're training the algorithm on the incorrect things. In supervised learning model development, domain experts are often needed to provide the classification labels. And if annotations are inconsistently, which is a common occurrence, that is something that I've even personally have gone through. It requires everything to be corrected. And due to the inherent also biases when you look at objects, especially when it's humans doing the work, there are potentials for inaccuracies as well as slips and other factors that may impact the accuracy of that data. And this is well known. It's a problem that everybody discusses, addresses, but the implications are very large. And while they have been mentioned, they have not been studied very well on then how to make sure that a lot of the labels can be corrected. And you can determine what are the true causes of the data label inaccuracies. But it's important that ensuring data quality in the annotations is crucial for the development. You need to make sure that the data is accurate to provide the correct training for those models. Now, as you progress with your training, obviously you might start with a bias towards a particular use case. But when you're doing focusing on a use case, there might be issues in the future as you try to expand that model into edge cases, or you try to span what the standard application of that particular model may be. Now, these situations will come up, and most of the time, the issue comes with the limited adaptability that you have within the models. If they learn from common scenarios, they're going to struggle with other situations. So it's going to lead to poor performance if you apply that model elsewhere. Also, for edge case scenarios, which are rare, atypical, something that is commonly seen in defense and aerospace, that becomes critical for models because then when they do get applied to these edge cases, they may not perform as well as expected. And then when it comes to diversity of scenarios and data, there's a wide range of it, including what are the rare occurrences and how do you improve the generalization of the model to potentially tackle some of the additional use cases that you may need. Which then goes into what are the computing considerations that you need in order to achieve that level of fidelity and accuracy within your models. And then how can then you prepare for future needs as you expand and the model becomes much more complex. And with all that, we cannot forget or discount the expertise that is needed. Most of the time, a lot of failures or lack of successes come in the fact that not all the expertise needed to solve the problem or to tackle the model training is present within a team, within an organization. Now, this may require different domain experts, from data scientists to data analysts to infrastructure folks, to be able to set up the pipelines. It's always going to be present there. In order to achieve your success, you need to be sure that you build the proper pipelines and make sure that everything that's needed for the domain experts to apply their expertise and technique, can be done. And most of the time, all of these expertise are absent. And while it's a rare case where you find an individual that can tackle all of these domains, it is very rare. So throughout the process, in order to achieve the success and value for the customer, it's important that the stakeholders are also included in what would be the data quality process to identify issues and make sure that as you move your project forward, there are no delays. So how can we overcome the 5 problems that we have highlighted? So let's go through a few recommendations. First, to tackle the data aspect, there is synthetic data. Now, synthetic data can come in many ways. Physics-based synthetic data is one that is used because it's generated using the physical models and simulations. It mimics the real-world phenomenon. It also applies the laws of physics to make sure that the data is reflected as accurately as possible. And this is very useful when it comes to real-world scenarios where you may not have enough data, or the acquisition of that data is too expensive, or it could just be risky to obtain that data. This also allows the validation of machine learning models in a controlled and safe environment, and it can be used virtually for prototyping, as well as predictive assessments of any kind of AI tools. When you see to the right, you'll see a workflow that kind of outlines the necessary steps required for the success of the use of synthetic data. Most importantly, is making sure that the use case and the objective is defined, because that's also going to drive the remaining steps and make sure that the necessary simulations and objects and environments are created that then are going to drive the remaining of the model training. Another recommendation is to adopt an engineering tool construct. And what this does is that it helps you create a repeatable process that is of high quality. It enables you to create the necessary data, also allows you to maintain maintain data provenance and history, and allows you to manage your high performance compute orchestration as needed, while integrating best practices to make sure that your computer vision workflows are consistent. This also makes it possible to experiment, iterate, evaluate, and also compare results as needed, and then repeat the process over and over again. And this iterative approach will allow you to revisit as often as possible and conduct as many tests as needed to gain all the necessary results for your projects. Obviously, the acquisition of fully annotated data is important. We've discussed some of the complexities of making sure that happens. With synthetic data comes the additional value that you can have accuracy and customization. The data can come 100% accurately labeled. And then once you create the pipeline, you can revisit, change parameters, and you can conduct further tests as necessary. And for example, that image that's to your right of the slide shows how the use of synthetic data can provide you the mechanism to create a simulation scene with various objects, but also accurately label them as needed. And of course, diversity is crucial. The inset that you see is one example of X-ray simulator, where it's actually changing the objects that are within the bag. The good thing is that synthetic data gives you the ability to add volume and diversity to your data set. Now, you're not constrained or restricted in any way. You can adjust for edge cases as needed. And if required, you can even go down the route of generalization. In this case that we're showing you in this image, you see that the objects are different in every case. And then most importantly, domain expertise. It can be difficult to acquire and have in-house. Models, techniques, workflows all require specific domain knowledge. Further add the need for domain experts in any use case in which you're attempting to create the model for. And it can be difficult to have an account for all these disciplines as you may need. So leveraging experts is the key to ensuring that you achieve things on time, you save money, and also improves your outcomes as you reduce the rework while leveraging domain expertise wherever needed. So Rendered.ai released a commercially available platform as a service for synthetic data that enables data scientists to overcome the costs and challenges of acquiring and using real data for training machine learning and artificial intelligence systems. The platform has been built for reusability, configurability, and reproducibility. So new applications can be built upon and share content, workflow, and compute resources. And the platform itself, as you can see on the slide, is comprised of two parts. You have the top, which are the applications, and the bottom are the tools necessary. So using the platform, customers can create tailored applications that we call channels that incorporate digitally simulated sensors, sensor platforms, and target content that can be objects as well as scenes. And these simulated assets can then be configured using a no-code web-based experience to control the output and the formats, annotations, and metadata, and distribution of specific assets or scenarios in output for synthetic data sets. The channels are used along with hosted job management capabilities to make sure that you can generate nearly unlimited data sets in a cloud-based high computing environment. And we'll show you in a demonstration how the channels can be used. Additionally, the platform includes developer tools, content management, source code samples. I already mentioned the no-code visual scenario generator, and then library management with history that includes management of your content as well as your 3D objects. It also has GAN-based domain adaptation, which is necessary to ensure the synthetic data gets as close as possible to the real data. The annotation management, which we can export in any format as needed, and the dataset characterization and comparison tools. Also, any third-party applications can plug into the platform using APIs. Also, any developer can create applications on top of the platform using our SDKs. And to demonstrate the ability of the platform to extend into a common AI workflow, Rendered right now offers AWS SageMaker as well as NVIDIA TAO integration, as well as a couple of other simulations. So I'm going to pass it over now to Dan, and he will go through a demonstration of the platform.
Great. Thanks, Ario. Let me share my screen. All right. So thank you, Ario, and thanks everyone for joining. So Ario mentioned the platform for synthetic data on Rendered.ai, and I'm just going to kind of walk you through what that looks like. Here we are within the platform. And as you can see, I've got a number of different workspaces here. And the power of the platform is that we can deploy custom simulation applications for specific computer vision use cases. So as you can see here, we have a variety of different use cases, different sensor modalities, different scenarios that we have hosted here that can generate really limitless amounts of synthetic data. So that can be overhead imagery, oblique imagery at sea, synthetic aperture radar. This could be hyperspectral or multispectral imagery using the Deersig simulator, X-ray imagery. Really, the sky's the limit for the types of imagery and the context within that imagery that we can replicate and simulate within this. So I'm going to jump into one of these workspaces, and by the way, much of these use cases you can see within the sample gallery. So if you sign up for a free trial, you can go over to our sample gallery and quickly create a workspace from these various different use cases and get started on the platform generating data right away. So I'm going to jump into one of these workspaces here, and to really understand how to configure our output data set, what we want to do is create a new graph. So I will do that now. And a graph is just a configuration of the simulation pipeline to output varied data according to the parameters that you set. So in this graph, this is the default graph for this channel. The channel is the application that gets deployed to the platform and hosts all that content and simulation capability. But here we have the default graph for this channel. We have a couple of 3D objects that are being added into the scene: an army truck and a tank. Before these get placed within the scene, we can modify those objects. So if we wanted to get more diversity within the objects of interest that we're interested in, to be able to account for various different cases where those objects might have different patterns on them, might have different types of dirt or rust or any sort of environmental variances from one object to the next. We can use what are called modifier nodes. And so this is a simple modifier node that is going to be applying a random pattern to this tank. And so every time a tank gets generated, it will choose at random from those different types of patterns. From there, we are placing these objects within a scene. So context is often very important within computer vision use cases. So we want to make sure that the context within the overall scene that these objects are being placed conforms to what we would expect in real world data. So in this case, we've got our grid cluster node here that is going to be placing objects in a rough grid orientation, similar to what you might see in a parking lot, but you have some variations. Not everything is going to be placed, right in a super square orientation. We're going to have some variation so that we have a bit more diversity in how these objects are placed. And then we want to be able to randomize the scenarios that these objects are in. So we have a number of different scenes here. We can choose to randomize those and choose to randomize how many objects are being placed. So the max number of objects within a scene, we can go over to our node library here and vary that maximum count here. So if we go over to a random uniform node, we can say, I want the max object count to be between 5 and 25 objects within each image. So I'll plug that in here. That's going to vary how many objects are being placed within a scene. And then similarly, we can control aspects about the sensor. So this is a simple sensor node. If you have a very complex sensor modality, there might be many more parameters that you'd like to expose, and that can all be modified and configured within the channel development environment. But here we can see kind of just the basic nodes, the basic parameters that we would want to be able to control here. So the look angle of the sensor, the azimuth of the orientation of that sensor in relation to the scene, the resolution of the output image, and then the size of the image itself. So we can also vary objects or parameters in here. So if we wanted to, say, vary the look angle between 0 and 15 degrees, we can plug that in. And similarly, change the azimuth of the collection between 0 and 360. We can plug that directly in as well. Similarly, we can change out the objects that we're interested in. So we have an object library deployed to this channel that we can easily swap out objects. So if, for instance, we're not interested in army trucks, we're more interested in construction vehicles, we can look at some construction vehicles. Say we want to add in a bulldozer. Now that will add in this bulldozer as potentially a distractor object. So if we're looking for tanks, we want to be able to add in objects that might be confused for a tank, and so a bulldozer could be a good distractor object there. Likewise, we can also, while we have all of these 3D objects deployed to the channel, we may also want to add in custom objects, and that's very easy to do within the platform. So we can, if we wanted to do that, we can go over to the volumes tab here. And volumes are basically cloud containers that we can just drag and drop files from our system. So content of various different content, likely 3D models in this case. So in this volume, we've added a model of a Nissan Patrol. That was something that we quickly added, and then we can just drag and drop that, similar to any of the other nodes that we've added here. So we can really customize how our data is going to look, what sorts of environments that we have that we're simulating objects within, what sorts of placement, what sorts of variations, so modifications. We wanted to look at other object modifiers here. We can see, if we wanted to vary things like, the color of different objects, or add rust or snow or any of these sorts of other object modifiers, that would be something we could quickly add and vary, and that allows us to better understand the impact that these different modifications have on our detection capabilities. So it allows us to quickly iterate on data generation to better understand how that data is best used within our computer vision pipelines. So once we have our graph all set, we can click the preview button, and that's going to generate a single image from the graph configuration that you've set up. So this is going to spin up an instance on the cloud, simulate the image, bring it back. It'll take a minute or so I won't wait around for it. But once you're happy with that output, we can click the stage button, and that's going to bring that graph over to our jobs pane. And so now we can see this is the graph that we configured. We want to be able to generate data from it now. So we can configure how many images do we want out of our data set. So if we want 100 or 10,000, we can specify that all within this runs category here. We can also control the seed number. So if we wanted to maintain the randomness from one data set to the next, but change one or two parameters or one or two nodes in the graph to be able to better understand the impact that those different those different variations have on our data set efficacy, we can control that randomness by applying the seed number, for instance, from the previous data set that was run. We can just copy that from our previous run that we can see here, and add that into our seed value. And then we can hit run, and we can see that that data set is in the process of being generated. We can see this is all being generated on the cloud using cloud compute instances. The number of instances that I have access to concurrently is set to 25. Since I'm only generating 10 images, that's assigned 10 instances to concurrently process the simulation of all those images. So it should take just a couple minutes to get that data set generated. Of course, if I generate 10,000, it'll take a little bit longer, but that's how we can orchestrate all of the compute behind the scenes to generate as much data as we need based on the number of concurrent compute instances that we have available. So once that data set is complete, we'll be able to see it over here in the datasets tab. So if we click on it, the data set here, we can see some of the preview images from that data set. So we can see just the image, or we can turn on the labels, the annotation that is included. So as Arya mentioned, fully annotated and accurately annotated data is important for CD workflows. That is all done by default on the Rendered platform. So all of the so 2D bounding box, 3D bounding box, instance segmentation, and instance masks, those are all included by default because we are simulating this data. So here you can see this aircraft in a variety of different scenarios with different sensor characteristics, different times of day, things like that. And this is a different object here. With that in mind, we have all that annotation, but we likely want to have it in our own specific annotation format. So if you have a project there where you're using YOLO or you're using Cocoa annotation format, and you also likely have your own defined set of groupings that your data should adhere to, what we can do is we can select this data set and convert, after the data set is generated, convert to various different industry standard formats. So if I wanted to convert to YOLO, I could do that here. And then I can specify a mapping file. So if I wanted to map various different objects within the data set to a certain class, for instance, if I wanted to map all construction vehicles to, rather than saying having them say bulldozer, backhoe, etc., map them all to a specific category. That way, we can quickly add that in the mapping file, and that can be created after the fact. So that's where the essentially the workflow of taking a channel, creating a graph, modifying the graph, creating a data set. From there, you can use that data set in training, but there's more that we can do to better understand the efficacy and to then also run post-processing on our data sets. So I can show you quickly what that looks like. So along with generating data sets on the platform, we can also upload real data sets. So here's what I've done. That's what I've done here. I have taken the XView data set, cropped a number of those images down. And in this case, we are looking for cranes, so construction vehicles, cranes within XView. So you can see these are some of the example images that we have within that data set that I've uploaded. I've uploaded 395 images here, and I've generated a similar amount of synthetic data. So this is the synthetic data with cranes and shipping containers, as you can see within these images. And what we want to do is be able to adapt the domain. As you can see, the image characteristics they look like satellite imagery, but they don't necessarily match the image characteristics of our XView data. So we want to be able to bridge that gap better. So one of the things we can do, we can train a CycleGAN model with the source set being the synthetic data, and our target set being our real data that we're targeting. Train that model, deploy it to the platform. This can be run as a post-processing step. So if I click here, we can see I've run this GAN model called XView on this synthetic data set. And this is the output here. So you can see this is my original. Here's my GAN adapted data set. So you can see the annotations remain the same, but the characteristics of the images they're a bit darker. They kind of match the hue and tone, and some of that sort of sensor aberration, the camera aberration that we might see in the XView as well. But I want to understand what that did in terms of the real embeddings in my data. So I want to understand how that maybe affects how a computer vision model understands and recognizes and interprets that data. So one of the tools we also have on the platform, if you select multiple data sets here, we can click this compare button here. And so that allows us to run a UMAP analysis. So we would select a fit data set. Typically that we would select that as our target data set, our real data set. So in this case, the X2, and run this comparison. So I've done that already to save some time. And we can see what that looks like. So what this analysis does is it runs these data sets through a pre-trained neural network, pre-trained on generic data, generic images, and then it runs those embeddings, those feature embeddings that are generated through that inferencing, and it reduces the dimensionality of that using the UMAP dimension reduction routine. So reduces those down to 3 dimensions so that we can plot them. So those feature vectors, high dimension feature vectors get reduced down to 3, but we can see relative to one another where they sit. And so we can see sort of patterns and trends within feature specs within that. So we can see from this that the blue dots represent our real data, our XView. The green dots represent our non-adapted synthetic data. And then the orange dots represent the domain adapted data. So we can see that right off the bat, we can see that the domain of the synthetic data is brought closer in line with that of the real data by doing that GAN adaptation. But we can also see some other trends. So we can see that in the real data there are outliers where these do not match those of the domain of those of either of the synthetic data. So we can inspect those, see what about those images are potentially out of cluster and unique. In this case, we can see a couple of these images are pretty dark. They may have lots of forest areas that we don't have in our synthetic data. But we can better understand, are these features that we need to represent within our synthetic data? And if so, we can go back and update our graph, update our channel, and iterate to better to create better synthetic data that more closely aligns with our real data. Or we can say these are not important features to us. This may not be something that we need to represent within our synthetic data. So it's a way to have a human in the loop to be able to analyze analyze and pick out patterns and trends within and between different data sets. And because this is a feature pyramid network, we can designate this feature size and see those feature embeddings at various different scales within the image. In many cases, they follow the same trends, but in some cases, we'll see those trends are somewhat different. So we can get a really good understanding of the different types of features that are detected within this data. So with that, I'm going to hand it back to Ario, and I hope this was an informative presentation. And I'm looking forward to answering your questions after.
Thanks, Dan. So we'll go ahead to the Q&A session, and we have a couple of questions already in the queue. The first one, how much time does using these tips actually save? And Dan, can you explain a little bit based on the experience the team has had with some customers already?
Yeah, so I think in terms of using synthetic data, the use of synthetic data can really enable performance that is impossible with when you're limited to real data. So in terms of time savings compared with using synthetic data, not using a platform like this, we've found that folks that have already had experience using synthetic data are able to iterate much faster and design those experiments much faster to better understand what synthetic data works best for their use cases. So when you're just using a simulation package on your desktop to simulate different types of data, that can take a very long time to and it's really siloed, right? So it doesn't it's hard for the simulation expert to communicate with the data scientists and for them to iterate towards the goal of perfecting that synthetic data. So really, in those cases, the time savings can be huge in terms of having that platform approach to generating data.
Okay. The next question is, how much does this cost? I'll tackle that one. And the way our platform is set up is on a fixed monthly subscription. That will depend on the amount of resources, assets, or simulators that you will require based on your use case. We also have the ability to help you and provide expertise as well as consultative services to help you identify the use case as well as any potential technologies or applications that you may have that may not be within our platform. So it's very flexible. Also, from a commercial standpoint, if you go to our website at Rendered.ai, we do have a pricing sheet for hosted platform. And then if there's any specific use cases on-prem or otherwise that you would like to discuss with us, please reach out and we can discuss. Also, we are aware that maybe the platform may not be right for you, so we can accommodate the creation of the data sets for you. Although in the past, what we've seen is as you iterate, it might be a more cost-effective option to have the platform.
All right. So the next question is, can I add our own 3D assets to the scene? So I touched on that quickly on the demo, but yes, we have a whole assets tab within the platform that you can create those volumes that I discussed, that I talked about. Drag and drop any content that you need up to those volumes and leverage those directly within the graphs that you have. So you would need to make sure that the data that you have is set up correctly to be used within the simulator that's used within that channel. But once that's done, it can be as easy as just dragging and dropping it right in.
All right, next
So, and
question.
then, yeah, yeah,
What's the best way to integrate the synthesized data into my systems?
yeah. So that is a good question. So we are the platform is uh, developed with API first in mind. So the idea that one can use the platform GUI to generate data and understand how to use that workflow that is valuable. But we also often find that customers need to be able to integrate this within their own production pipelines. So with that in mind, we encourage folks to use our SDK to drive synthetic data creation, as well as all of the downstream integrations that go into that. So definitely, push our customers to use our SDK as much as possible.
All right, thanks, Tim. Any other questions? We have an open queue. If you would like to learn more or discuss further any other topics that we have covered today.
All right.
All right. Well, thanks. Today, we discussed the 5 common issues that impact success of computer vision training to achieve a performance state. We provided a brief overview of each one. We discussed a few considerations that can help and prevent or overcome these issues, as well as provided a solution for your consideration as you tackle future computer vision workflows or issues. If you would like to learn more about what we do, Rendered AI, and more about our platform, or any questions for me or Dan, please reach out to us. The information's on this slide right now. We'll be happy to set up any individual demonstrations, conversations, as well as provide you additional information specific to your use case. Thank you for joining us today, and we hope that you have a great rest of your day.